So I wanted to show you the story of the James Webb Space Telescope, but also to give you some of the context behind it. So to summarize, here is the great telescope looking straight at you. Its big golden hexagon is 6.5 meters across. It is protected by a 5-layer sunshade, which is as big as a singles tennis court. And it will be launched according to plan on Halloween this year, October 31st, 2021. And within 6 months, we should be able to show you wonderful data. The beginning of science operations will occur around end of April of 2022. So as you know, this is a joint project of 3 space agencies, NASA with European and Canadian space agencies. And I'll show you a picture of our science team in a bit, just to emphasize that one of the instruments for the Webb telescope was led by Gillian Wright at the UK Advanced Technology Centre in Edinburgh. So here's a picture of the telescope. We'll show you more about it later, but just to emphasize, it is open to everyone around the world through a proposal process, and it has taken many thousands of people to build it, and we are not that far from launch. So, okay, computer, do the right thing for me. Okay, so I like to start with the questions that bothered me when I was a child and got me excited about science and astronomy. So now we know that the universe started out smooth and hot. This was known, and the theory was developed just around the time that I was born. I was born in 1946, and in 1948, the publications came out from people right here in DC. To say, yes, indeed, the beginning was hot. We can calculate how hot. We can calculate the temperature that it should have now. And so that was just after I was born. So we know this is now a story to tell. We know that the early universe was unstable and has reorganized itself into complex systems over and over again in a huge hierarchy. We know the universe is probably infinite, although no one could possibly prove that. And that it is very old, if 13.8 billion years sounds old to you, which means that there's even rare possibilities like our own discussion, our own existence has had time to develop. We have come to understand about stored information. The DNA in our cells is a digital code, and it is decoded by special code readers in the cells. So a pretty astonishing story that each of us has got 30 trillion living cells, each of which is a digital computer communicating with the others. You don't think about it that way when you say, am I going to get my grant or my scholarship? But it's a pretty astonishing story. It means that we understand a little bit about evolution, and I call it here survival of the lucky, because when evolution was first discussed by Darwin, people said, oh, obviously we are the best. We are survival of the fittest. We are the top of the pyramid. We're the best. But actually, we know now that we are also lucky because for whatever reason, our population was down to maybe a few hundred or a few thousand individuals, maybe 100,000 years ago. And if they had failed to survive through that, we wouldn't be here. So there's an awful lot to think about there. We have learned that each one of those individual cells is stabilized by feedback loops. If you're an engineer, you say, how am I ever going to build such a complicated thing? And of course, it's been done by trial and error over 4 billion years of life. Biologists call this homeostasis, so that even though almost all of our atoms have been replaced over and over again, nevertheless, we have individual identity and even memory. So even though most of my cells are replaced, I still remember a little bit what happened when I was a child. So now to put a little more science behind this, so we have learned that there's a sort of standard theory of particles. We have quantum mechanics that tell us that the way that the building blocks fit together, the shapes of the building blocks and how they fit. We astronomers have tested out gravity in a remarkable way. It's not just a good old 1/r² force that makes things happen. It is the instability that makes things happen. So we know, and other people don't always appreciate, that gravitational energy can be released as things become pulled together by gravitational forces, which means that a lot of things that you think you learned in school are untrue. Gravity makes material self-heating. It warms itself up. It has a negative specific heat, which means it is unstable. A pretty fantastic story to be telling, and we astronomers are the ones who know about this the most. Of course, we know about equilibrium thermodynamics that tell us that if you make an orderly thing like a crystal, it is done by increasing the disorder somewhere else. So this is all in accordance with what we learned a couple of centuries ago about thermodynamics. But now we're beginning to appreciate that non-equilibrium thermodynamics is also important. Whenever there's a gradient of a temperature or of an energy flow, it is possible for nature to find a way to increase entropy with a spontaneously produced heat engine. And we ourselves are examples of spontaneous heat engines. We increase the entropy of the universe by doing what we do. You may not like it, but that's how we do it. So we've known for over a century how to calculate some instabilities. James Jeans told us about this one. And so we look out into space and we say, how are we going to calculate all of this? Well, that picture that I'm showing you there is way too complicated to answer with just James's calculation. So we're going to have to use a computer. So just to review a little bit of history to put this into context, this is something you know perfectly. But in 1929, Edwin Hubble gave us the picture that showed the universe has an age because distant galaxies are going away from us with a speed proportional to distance. And of course, there's a mistake on this plot, which is that his distance scale was off by about a factor of 7. Using Cepheid variables to get this distance scale was misleading because there was more than one kind of Cepheid variable. And of course, he couldn't tell that. At any rate, age of the universe was about 2 billion years, according to him. Now it's about 13.8. Curiously enough, you probably know that Einstein was not persuaded when he saw this chart. He had to be shown the error of his theoretical calculations before he would really believe. And by the way, the error of his calculation was that his proposed answer with a cosmological constant did not produce a stable universe. His universe that he wanted was unstable. So anyway, just to summarize the standard picture, I put this here because so many people don't actually understand it. We know in the standard picture that the universe was very hot and very compressed, and that it has no center or edge, and that it's expanding into itself. Quite a lot of people run into confusion when they point out that there is no first moment in this story. The time equals 0 is not included in the standard story because, well, there's the same way as there is no smallest positive number, there is no smallest amount of time that we can calculate with our current understanding of physics and math. So although people talk about the instant of creation in popular science, it is actually not quite true. We only have in physics, as I understand it, the way of describing process, where something changes into something else according to some ideally descriptive law of physics with the mathematics behind it. So people tell it wrong a lot. And so when you get people coming to you and saying, well, wasn't the universe compressed into a point and it exploded for some unknown reason, that's actually all wrong. The universe was never compressed into a point. As far as we know, it has always been infinite. So you can argue about it. We couldn't possibly prove that. But at any rate, this is a better picture than the one that people talk about when the universe was compressed into a point. Nah, that was not true. So how are we going to know if this story is true? Well, we take pictures. Hubble telescope was launched just in April of 1990, so it's almost 31 years old. As you know, it had to be fixed before it could really get good pictures. Then they did. So after they got the good pictures, people said, let's write a book and tell us what we should build. So here's the great James Webb Telescope. We are doing what they said in a little book. The little book was called HST and Beyond, and it was written by a committee with a brilliant poetic editor, Alan Dressler. So anyway, here's the telescope in space. It is, as we mentioned earlier, an international partnership. We are leading the partnership from Goddard Space Flight Center, just outside Greenbelt, Maryland, just in Greenbelt, Maryland, just outside Washington, D.C. And we have had contributions from around the world, especially including Europe and Canada. Europe contributed a mid-infrared instrument, as well as the near-infrared spectrograph, and both have been successful. Both were troubled, but to tell the truth, the mid-infrared instrument was the first one to be completed. So congratulations to the UK Advanced Technology Center team and Gillian Wright, who made that happen, coordinating the efforts of well over 15 European institutes to make that happen. So there are several main points about this. The telescope is cooled to low temperature. The primary mirror there is around 40 Kelvin. Will be, and it has an instrument package that's at 40 Kelvin and also at 7 Kelvin for the mid-infrared. It is going up on a European supplied Ariane 5 rocket in October, and it is going 1 million miles, 1.5 million kilometers out into space, beginning on that day. We are carrying fuel, by the way, for a 10-year mission, and we think if we're lucky, we'll have more years than that. But of course, space hardware has its own ways to fail, so we can't promise it and prove it. We are just hoping for it. So just to repeat a little bit of the story of how we got here, here's a picture of the book. There's Alan Dressler. And when I read that book, I thought, oh, that is the most exciting thing I could possibly imagine working on. And so this is Dan Golden. He announced to the American Astronomical Society in 1996, in January, that we are going to build this telescope. And he said, why such a small telescope? How about a bigger one? So he got a standing ovation. So we kind of thought, well, this is obviously a popular plan. Somebody might need to mute out there. We're getting echoes. Anyway, then in 2000, the decadal survey that we do endorsed this as their top priority. They and we all believed the project was a little easier and quicker and cheaper than we ended up being. But I think the fundamental reasons why it was the top priority are still true. Then in 2010, we built another decadal survey around the planned success. Of course, we thought we would have this launched by now. But anyway, here we are in the ideal picture of the Ariane going up with a telescope in the top. So there are 4 major science themes that our science team declared at the very beginning to guide us in the choice of instrumentation that we would decide to build and negotiate partnerships around the world to produce those instruments. So here are they illustrated briefly. And of course, this turned out to be true. When we received proposals for observing time, that's pretty much what we are going to point at. So just to illustrate our science team, some of the folks here you know. There's Gillian in the lower right-hand corner. There are several other European scientists on this picture, some working in the United States, like Massimo Schiavelli. Anyway, Europe has a major role in not only producing the hardware, but also making sure that it will operate properly after we launch it. So anyway, there's our science team currently. It's a big team, and it's about what it takes to make this thing go. And this is also a small fraction of the total number of scientists working today on the project. So here's the design of the telescope. It is called a 3-mirror anastigmat telescope, which means it's got a big elliptical primary, very short focus one, a convex hyperbolic secondary, and then there's an elliptical third mirror that compensates for the aberrations of the other two and give us a very large field of view with excellent image quality. The requirement is that it should give diffraction and limited image quality at 2 microns. And that we do expect to be a little better than that because we've had engineers protecting that specification. So how do we do it? Well, we have made that mirror, the big mirror, out of 18 beryllium pieces. And each beryllium mirror is about 2 millimeters thick with ribs. And each one is adjustable, rigid body degrees of freedom plus the radius of curvature, so that after we get this launched and cooled, we will be able to focus that primary mirror and make it behave as though it is a single, almost monolithic primary mirror. So there's a huge technology behind this, including what we call cryo-polishing. It means that you have to measure each mirror segment when it's warm and measure it again when it's cold. Then you have to calculate what bumps to polish off so that when next time you cool it off, it will be the right shape. So we did that, and they are all brilliantly wonderful, good mirrors. Each of them alone is far better than this specification of 150 nanometers RMS. But of course, that's not the only part of the system. So it's done, it works, has been thoroughly tested. So here's the instrument package, 4 instruments. You see 2 of them coming from Europe and 1 of them coming from Canada. And 1 of them is all from the United States. Well, although all of the detectors come from the US, and the remarkable special piece part for the near-infrared spectrograph, the NIRSpec, comes from the US also. We have a micro shutter array on that instrument, which allows you to choose 100 different galaxies at once to get the spectrum. So very general purpose instrument package covering everything from 0.6 out to 28 microns. We are just barely able to reach the hydrogen line at 28.3, I guess it is, microns. Excuse me. So each of the instrument teams, by the way, that submitted an instrument also got allocated some observing time. So they've all declared what they're going to look at also. So how good is it? Well, it's extremely sensitive. If you imagine yourself to be a 1 square centimeter bumblebee at the distance of the moon from the telescope, you end up as a source measured in nanojanskis. And a time exposure with this telescope can observe such a small thing, both reflected sunlight and thermal emission from the little square centimeter. Our harder problem turns out to be observing bright objects. Excuse me. But we have worked as hard as we can to use the same equipment for bright objects, using special modes of controlling the detectors to read them faster. So it means that we can observe all the solar system objects from Mars on outwards. And we can do transit spectroscopy for all stars except the very brightest ones. So just to give a little more quantitative view, you can see our graphs here illustrating how much more sensitive we are than other telescopes have been. So here's the Webb telescope imaging sensitivity way down here, and we reach about 10 nanojanskis in 3 hours. So that's pretty astonishing. And it's much better than anything else has ever been. On the right-hand side, we have spectroscopy. It's also far more sensitive than anything else has ever been. So the upshot is, even if you only get 1 observing minute with this observatory, if you point it at the right thing, you could get lucky and be able to write a science paper. So just a sec, I need to get a little water here. Okay, I'm back. So this is once we explain on this chart what we're doing with our observing time. So the guaranteed time observers are the ones who either developed hardware or software for the observatory or made proposals to NASA headquarters for interdisciplinary science. So they got their 4,000 hours and they declared a long time ago what they were going to point at. Then we solicited proposals from our community for what we call early release science. And we got over 100 proposals for that, but the definition of these programs would be that all the data have to come out immediately so that everyone who's preparing observations for the next round will have as much information to go on as possible. And we are now in the process of setting up our review for the next batch of proposals that were received in November. And we had a huge number of proposals, and we are doing something called a dual anonymous peer review, which means that neither the proposers nor the reviewers, we make sure that the reviewers do not know who the proposers are. And so we're trying to make sure that the proposals are reviewed based on the quality of the proposal and not on who somebody thinks someone is. So this has been quite successful. In the times that we've done it with the Hubble, we have felt that the results were much more fair to everyone, and the number of women PIs went up when those rules were made. So pleased with that process. So what are we proposing to do? Well, this is a summary of what people think they want to observe, and according to how much time was proposed. About a quarter of the observing time proposed for galaxies. And anyway, that's one of the biggest sections. One of the exoplanets, 25%. Galaxies looks like a quarter, but the chart label says 20%, so it can't quite be right. Anyway, you can see that every subject has gotten a lot of observing time. The solar system might actually get as many observations, but it doesn't take very long to observe bright solar system objects, so they don't need a lot of observing time always. So coming up soon, we will have a review process. Hundreds of scientists will be called on to be on our committees, and we hope to be able to announce soon after that what we're going to point at for these observing proposals. By the way, almost a third are from European proposals, European PIs. So how are you going to keep up on what we're doing? We have a YouTube channel these days. So you can find practically everything that we're doing. If you'd like to hear and see verbal descriptions of much more about this, how to read our documentation system, how to write proposals, the planning tools, the APT, all those things that you would perhaps want to know about. There are instructions on how to analyze data with Python tools that we're building, and so on. By the way, all the data will become public, so even if you did not propose, you'll get to see the data. A lot of the data are protected for a year, but they eventually come out. The early release science data will come out immediately. So what are we going to look at? Of course, the first galaxies. This was a picture that said, please build us another telescope that can see infrared. So the point of the calculation is, well, the first galaxies were not visible to the Hubble because they were too far away, too far back in time, too red-shifted, and too faint. So even the smallest little red specks were not the first galaxies on this chart. Now, what are they going to be? Well, who knows? We think that they will be like this, that the first galaxies were produced by molecular hydrogen cooling at a redshift of something like 25. If this curve is to be believed, then ordinary atomic cooling could start working around a redshift of 15. So if this story is true, we'll find out. So how are we going to find out? Well, of course, take lots of pictures, take lots of spectra. So here's a map illustrating the proposals that were already proposed for observing with the NIRCam, that's this near-infrared camera, and a multi-object spectroscopy. So the main point of this one is it's a good and thorough plan. So when those data come out, everyone will analyze them and expect it to be very exciting. Here's a sketch illustrating our multi-object spectrometer. In the lower half of the picture, you see these little rectangular slots where we can open up a slot to allow a galaxy or something into our spectrometer. Now we have to choose very carefully which ones to open so that the spectra do not overlap with each other, but we do know how to do that. So what are we going to look at in the infrared? Also, we'll be looking into dusty clouds where stars are being formed. This comparison of the infrared picture and the visible picture from Hubble shows you a dramatic difference. Of course, the main advantage of the infrared is that the longer wavelength infrared light will be able to go around dust grains instead of bouncing off. So the opacity is much reduced. Even, however, with the Hubble infrared capability at 1.7 microns, you see these dust clouds are still quite opaque. So this is a sort of another visualization of the difference of appearance when we change from the Hubble visible band to the Hubble infrared. So you know it's going to be valuable and important to make a map showing how this changes into the mid-infrared that the Hubble couldn't see at all. We will certainly be looking even in the solar system. As you know, we've got a lot of interest at NASA in the solar system. We have been to visit Europa and Titan, and we are planning to go back. Our next mission to Europa will be not a lander, but an orbiter. It is hoped that we can fly through the jets, the water that are coming out from between the cracks in the ice flows. Very long term, people would definitely like to land on the surface and get detailed examples and chemical analysis of whatever is coming out. If the ocean under that ice is alive, then you might be able to tell by examining the water that comes out. On the right-hand side, here's a map of Titan as seen up close. Again, we are going back. We have a lander that is planned. We'll use a little helicopter that stores up energy from a radioisotope thermal generator into batteries and is then able to fly short distances around this satellite, because the atmospheric pressure is about 1 Earth atmosphere and the gravity is a lot lower, so it's not as impossible as it seems. So this is an interesting place to examine because, among other things, if you think that life might not require liquid water but could possibly use another solvent, then this is the place to go to find out, because this is nature's experiment on mixing liquid solvents of hydrocarbons with water and everything else that might be interesting to create another form of life. Do you think it's possible? I don't, but you never know. You should look. So we'll certainly be looking at exoplanets in this way. This is a transit spectroscopy. The apparent diameter of an exoplanet as it goes in front of its host star actually is wavelength dependent. And so by mapping that, we're essentially probing the atmosphere of an exoplanet. We have in plan already to observe 9 Earth-sized exoplanets, 5 Neptune-sized exoplanets, and 16 Jupiter-sized exoplanets. And we know exactly when they're going to go transiting in front of their stars, and we'll be looking at them. We are not currently expecting to be able to detect water. Sorry, I meant to say oxygen. We certainly do hope to detect water. So we're not going to be likely able to say, yes, that planet's a lot like Earth, but it'll be interesting to keep on looking and to develop our understanding of other planetary systems in this way. I think there could be many surprises. Do not know, but one of my friends here at Goddard says exoplanet science is still looking for its first successful prediction. For almost everything that we know has been a huge surprise. And I think many more surprises are likely to come in this area. So there, as I mentioned earlier, there's an early release science program where the data will become public immediately. We had a lovely collection of proposals, and there are recorded webinars if you want to hear overviews of all of these particular proposals, so you can get your minds ready to analyze the data as they come out. So here are some examples of them. We have several on distant galaxies and the first galaxies. Jane Rigby has a plan to study highly lensed galaxies. There are many. There's oh my, my fonts have fallen off the bottom of the page. But at any rate, we know where to look to try to find some of these examples. Mostly people have said we should go look in the places where we already know something, because those data are valuable. But that's not the only way. We kind of imagine that our tool is so powerful that even if you don't know where to look, something will turn up. So we have other programs to look at nearby galaxies where we can see the details. We're going to look at the nuclear dynamics of a Seyfert galaxy. Misty Bentz will do that, and her team will be looking at resolved stellar populations nearby. The telescope is so much bigger than we have had in space before, and the angular resolution is about as good as the Hubble, or even better in places. So should be able to learn a lot about individual stars out there. Be looking at the quasar hosts to see what are they like. So integral field unit spectroscopy in the mid-infrared is going to be exciting too. Lots to know about that. So astrochemistry, several proposals to do that. Wolf-Rayet stars are making dust, going to learn about that. Look at the ices forming around new stars. We do know how to attack that problem. So lots of fascinating challenges here as well. We'll be looking at planets, the Jovian system and exoplanets both. So just illustrating, as I mentioned earlier, that we can get spectroscopy of other planet atmospheres by the transit spectroscopy method. We already know the technique can work, but we don't really know what nature has given us to see. That's why it's exciting. Here's another example. This is a plan from the near-infrared, NIRSpec, the team, the imaging slitless spectrometer team. This is the Canadian team that produced one of the 4 instruments for the Webb. They've identified a list of targets to observe that way. So some of them are quite small, down to the mass of Earth. Some of them are much larger. So we have many choices of things to look at. So how are we going to get our observatory up into space? I'd love to tell you a little bit about our engineering program, because that's what we've all been concentrating on for such a long time. First, we put the telescope together in the clean room at Goddard. There's the great golden hexagon. And after we put it together and made sure it was properly aligned and all the motors would work and all of that, then we put it in a shaker. It is protected inside a gigantic plastic tent. And we put it on a shaker capable of providing 50,000 pounds of oscillating force to see if it was going to survive launch. So it was a pretty tricky test. We had to go quite slowly through it, but we did learn what we needed to learn, and we did not break it. So then we put it in a shipping container. Looks like a giant mailbox, but much larger. And so we drove it around the highway to our Air Force base nearby, Washington, D.C., and the entire shipping container and the truck drove into the aircraft. It's a C-5C aircraft, about the biggest one there is. And it flew to Texas, to Houston, where we have the Johnson Space Center. And we put the telescope with its instrument package into Chamber A, which is the vacuum chamber that was built originally for the Apollo astronauts to practice going down the ladder of their spaceship onto the surface of the moon. So it's on the historic register, and it's an enormous facility, but just about the right size for our telescope. Then we put it back in the airplane, flew it to California, and it has been attached to this portion, which is the warm part of the observatory, the sunshade and the spacecraft bus and all of its electronics and rocket engines and all those things. We have put the combination through its final vibration test, and it is now more or less like this, and we're about to start folding it up to put it back in a shipping container. It has a different shipping container. It's a special ocean-going barge that will be capable of taking it all the way to the launch site from Long Beach, California. So there it is. This barge has been through the Panama Canal before, and we will be too. The Webb telescope goes through there in order to reach the north coast of South America, where the European rocket will be launched from the Ariane space facility in French Guiana. And there's a tiny version of the picture of the telescope folded up in the top of the rocket there. Then we push the button around Halloween, and then we will, with any kind of luck, have it fully deployed in a few weeks after launch and on its way out to deep space. So this is where we're sending it. We're sending it to the Lagrange point 2. It's 1.5 million kilometers farther from the sun than we are. And the point of this place is that from that location, the sun, the earth, and the moon are all in the same direction. You can put up a single-sided umbrella and protect the telescope from the heat and light of all of those objects, and it'll be dark at the telescope and cold. Here's our scary movie. As you know, when we landed on Mars last time with our 7 minutes of terror, that little bird had to do everything all by itself without help. It had to respond without the ability for us to send any commands to correct for anything. Here is our very large, complicated observatory unfolding in space, and this is done step by separate commands from Earth. And at every step we stop to see, did that work? And if it didn't, we have a second way to accomplish every step. So for instance, every electric motor has 2 sets of electric windings and 2 controllers. If you look at this, you say, that's amazingly complicated. And how can you possibly do something that complicated? But when we chose the company Northrop Grumman to build this, they said, oh, definitely this is not the most complicated thing we've ever built and flown. And they've all worked. So that was a good sign, but it's still very complicated and it's still very difficult. It means that every step that you're seeing has been rehearsed numerous times, and we have still to make sure that we do it right. There is actually no current capability to go help the observatory in case something goes wrong. So we have to make sure everything that could go wrong has been tested. And one of the reasons that it's taking us so long to do this project is that there is absolutely no room for mistakes. Or maybe I should say no room for mistakes that are not found. Have to find them all. So you can follow this project with numerous things on the web now, as well as I showed you that we have a YouTube channel. There's a vast amount of information available for people who wish to know the details or just to watch overall, and all the data will become public. So that's the web. I want to show you just a few ideas I've been working on for what can follow after this, because the Webb telescope is an amazingly expensive, difficult, and long-term project, and we haven't yet made up our minds what are the next observatories to put into space. Well, we are already building 3 gigantic telescopes on the ground. So here they are. The one that is farthest along is the European one, the EELT, 39 meters across. It is about 6 times as large as the Webb telescope. And so it will do what you can do on the ground, and it's probably the biggest thing we're going to do for a good long time. So I've been interested in how could you make it even better. So one of the things that it will have, of course, is adaptive optics to make sure that it gets the sharpest possible image quality. And this is really tricky, especially at the visible wavelengths where you don't have very many things to focus on. So I've been working on this topic. Of course, the idea of adaptive optics was conceived by Horace Babcock in 1953, but nobody could actually do it then. In recent times, we've got this quite well perfected, and it is, however, limited by having to have something to focus on. You have to be able to sense whether the telescope is correctly focused, and you need a star out there or something like a star. And so we are limited in this area by the availability of stars to focus on. We can produce some artificial ones in the upper atmosphere, but they're not as good. So anyway, that's one of the questions I've been working on. This is a point to point out, however, that when you go to see your eye doctor, they have technology that derives immediately from the Webb telescope technology. The person who figured out how to measure the Webb telescope mirrors as they were being produced and get them to be perfect said afterwards, well, I know how to do this next step, so you can go to your eye doctor and get better adaptive optics there. So he did that. So when you go to your eye doctor, if you need to go to get better eyesight or to get corrected eyesight, thank the Webb telescope team. So here's an idea I've been working on recently. An orbiting configurable artificial star. Let's shine a laser beacon down on Earth, pointed at the observatory, to make sure that there's always something to focus on when you want to do adaptive optics. And with this idea, you should be able to do it at all wavelengths and not just infrared. So definitely worth trying to work out, and we are developing this as an idea now. Just to imagine what you could do with that. Well, suppose you could do it even better. Suppose you could put a star shade and cast a shadow of a nearby star onto the telescope while you're running adaptive optics. So here's a sketch illustrating that if you could do that, then you could get this little picture on the right-hand side with Earth, Venus, and Mars in a 1-minute exposure from the EELT telescope. It is pretty difficult to imagine how to do this, but I think that means there's work for the next generations of scientists and engineers. So let me conclude here and say, if you could do that, you could get wonderful spectra as well. Despite interference from Earth's atmosphere, you would be able to tell if a little Earth out there has oxygen and water in its atmosphere. So not impossible, at least not impossible to dream about. So wish us luck with this idea, and we hope to get it published soon. So time for questions.